So I'm gonna now, Don has an announcement to make about a role he's got at Reasons to Believe. So I just want to pass it over to him. Go ahead, Don.
Thanks, Bruno. So, Hilmar, you'll be particularly interested to hear this, but most of you have heard of Reasons Institute, which is a online forum for training and education that is a ministry of Reasons to Believe. And it's through the Reasons Institute that they offer the courses on, the Bible and science, creation and evolution, etc. The different courses that you need to take if you want to become a certified apologist with Reasons to Believe. And they have a number of other courses as well, courses in astronomy and astrophysics, et cetera, which are geared for the layperson, but does require a bit of a stretch when it comes to, science. So there's a number of books you have to get and readings you have to do. And Reasons Institute has expanded now to offer different types of courses. So for a given course, you can take it just as an audit, like you can just audit the course, or you can do it for a certificate in apologetics, or you can do it through Biola University as an actual course credit for an undergraduate program. And so there's different options available to the student that's doing it. For each course, there's a professor, typically one of the scholars or adjunct scholars from Reasons to Believe, and then there's an instructor. And the job of the instructor is basically to track all the students, make sure that their assignments are in on time and graded, participating in online forums for the students, helping them to understand concepts that they might bring up in the forums, et cetera. And so I've just recently become an instructor for the advanced seminar on biochemical design, which is a course that I believe Hilmar took last year. And so that's been a really nice thing to do. It's stretched me a little bit in terms of questions you get asked and grading assignments and so forth. So that's been kind of cool. And it's interesting because this course is essentially forms the basis of what Fuzz is going to be speaking to us about tonight. He will be talking about his new book, Fit for Purpose, but it also builds on his other books like Cells Design, Who is Adam, and Creating Life in the Lab, and also Origin of Life. So there's a number of books that kind of form the basis of this particular course. And so there's a bit of reading involved. Like I said, there's assignments you have to do on time and so on if you want to get credit for this course, either at a certificate level or as an undergraduate student. So it's kind of neat to jump in and be part of this particular course. It certainly fits with my own background the best, but even so, I've had to dig out my biochem texts a few times to brush up. So that's been a good challenge. And I don't even know if Fuzz knows that I'm now the instructor for this course or not. We'll find out when he comes on, but I won't bring it up. But anyway, the point is, it's been really great to get involved in this way, and kind of expand my involvement with RTB. And just want to encourage you to check it out. Go to the Reasons website and or just look up Reasons Institute, and you can see all the courses that are offered there when they're offered. It's not like, you can just do it at any time you want. They run these courses on specific semesters and things, so you need to sign up. So check it out. And that's my report. Thanks, Bruno.
Don, are you currently teaching the course, or is it going to start soon?
No, it's already into the fifth and sixth week. So I came in after the course had started. They didn't have an instructor, so when things fell into place for me to come on board, it was good timing, but I had to catch up a little bit, which was no problem. So yeah, it's up and running.
Do you know when the next one is?
Well, this is the spring of 2022 course. I think they have a fall one as well. They typically don't run these over the summer for obvious reasons. So I think there'll be another one in the fall. That would be my expectation. Hilmar, when did you do yours? Do you know? Was it spring or fall?
I think mine was in January.
Okay.
Started in January. Yeah.
Yeah, that's the spring one. Yeah.
So I did the other biochem seminar in December, and then I did the one in January, and it was too much.
Yeah.
But I found the biochem design was actually, for me, was better because it started from a more basic approach. It didn't assume anything, even though it was quite a stretch. I found it better than the other advanced biochem seminar. I forget what the name is. But I don't think I'll be doing those for a little while. So, but I enjoyed all the courses. I've done 10 courses now, and everyone gave me a lot. I found the interaction with the other students and the instructors was just amazing, and you get to use the concepts interactively with other people, and that really helps you realize what you don't know and understand more. So sorry, too much information, but there you go.
No, that's great. Thanks for sharing that, Hilmar.
As I mentioned, Fuzz has a meeting he's attending before this, so he's going to be a few minutes late. So in the meantime, I just wondered if anybody had any questions from last meeting. Where is this thing here? Where did it go here? Oh, here we go. So I don't know if you were attended last month, if all you did or not, but I did a presentation giving everyone an overview of the anthropic principle. Does anybody have any questions from that they thought of after last week? After last month's meeting?
Bruno, I had one question. You said, this is on a slightly different subject, but you said that our sun is only producing helium at this time. And I thought suns that were this size that we have would end up in their life cycle producing up to iron. You know, they would keep on getting hotter and smaller and all this, and they would keep on producing higher and higher elements, but they would stop at iron. It would go cold and be a white dwarf or whatever. But you mentioned about our sun, and you said it just produced helium, which is true at this point in time because of the temperature of it. But do you think it will ever produce anything more than helium, or will it go into a red giant and then whatever?
As far as I understand it, as it gets closer to the end of its life, before it goes supernova, at that point, it will start producing some higher elements, but I don't think it'll go up to iron until it actually goes supernova. If anybody knows the answer, they can correct me. For sure.
Well, it's too small to go supernova. It's not big enough.
Yeah, which I was going to say, our star won't supernova. It's not big enough. And that's where you get all the really complex elements, is in supernova events. But yeah, it's a good question. At the core of the sun, I don't know if it is potentially with the gravitational forces there, whether it actually is creating small amounts of some of the lighter elements like lithium, for example.
According to this chart that I found somewhere, the sun will turn into a red giant first, and then it will shed the outer layers on the outside of that, and then it'll contract to a white dwarf. So it won't go supernova.
Right.
But I think at the point when it becomes a white dwarf, it will start producing other elements besides helium. I don't know which ones exactly.
But when it produces a white dwarf, it doesn't do anything. It stopped doing anything. It just simply, it's just frozen. It just
basically
cools down.
If it's able to attract other material, like if the sun actually was a binary system,
Yeah, well, that would be
turn
different.
into a white dwarf, it would attract hydrogen from a nearby the star that goes around it, and
Right.
eventually it would increase in mass to be 1.4 times what it is now, and at that point it would go to a type 1 supernova.
Yeah, yeah.
But it's not a binary star, so it will never have enough material to do that.
No.
Right.
Most supernovas come from much larger stars.
Yeah, this diagram gives you a
The bottom one, the bottom diagram, yeah.
star that's 8 masses of the sun, or anything bigger than 1.4 would go supernova eventually.
Yeah, what's that about fluorine? Does a star the size of our sun not end up producing fluorine when it produces and it goes up to producing iron?
Only if
So-
it's a binary system, where this is the white dwarf at the bottom, and the one above is another star and the material from the other star is being attracted into the white dwarf. And on the surface here, as this other material orbits around, it produces fluorine. And this is apparently the only way to produce fluorine in the universe. It's not produced during a supernova.
Really? Well, that's interesting. So
I
basically,
just wanted to make a quick comment, Bruno. I really appreciated you adding the comments to your presentation in writing and just sending them out. I haven't had time to watch that episode yet, but I really appreciated that, and I thought the presentation was really good. And I was going to make that comment last gentleman made about the producing higher elements than helium, but yeah, that's my understanding is that the last element to be produced will be iron, and at that point the sun starts cooling down and it becomes a white dwarf. Sorry about
Oh, here comes Fuzz. Fuzz is joining us now. Let me stop this sharing here. Hey, Fuzz, are you there?
I am. Can you hear me?
Yes, I can. How are you doing?
Good, good.
Everyone's expectantly waiting for you.
Good. Well, thank you so much for letting me join a few minutes late. So it's much appreciated.
Whenever you're ready, are you ready to begin, or do you want to get yourself organized first?
I think I'm ready to begin. I'm just going to close a couple of windows to make sure. And then I should be able to share my screen, right?
I'm going to make you a co-host here. Hold on. You should be able to do it now.
Okay. Well, let me go ahead and share the screen. And then is everybody able to see the screen okay? Does it show up?
Yeah.
Perfect. Yeah.
Perfect. Okay. All right. Well, again, thank you so much for letting me join a few minutes late. We are rolling out a new management software or management system here at RTB. And so we're going through a series of training, day-long trainings. And so I ended up bailing out of the last part of the meeting to do this. So thanks again for allowing me just a few extra minutes. I much appreciate that. And thank you also for, of course, inviting me to your meeting this evening. I really appreciate the opportunity to talk about my latest book called Fit for a Purpose, which is an exploration of the biochemical anthropic principle. Does the anthropic principle apply to biochemical systems? Do we see anthropic coincidences when we look at biochemical systems? So again, very much appreciate the opportunity to talk about the book. And I also just want to say, before I get started this evening, how much I appreciate all of you. And we're so grateful for the chapters that we have, not only in the US and Canada and other parts of the world. It's really touching and meaningful to us to know that there are people who are willing to devote their time and their energy and their resources to partner with us. And for those of you who are part of the chapters, you have gone even beyond that, where you have even made our mission your mission, that you've made our calling your calling in ministry, and that means a whole lot to us. So thank you so much on behalf of everybody at RTB. Again, I just want you to know how much we appreciate all of you. Okay, so I'm going to get started this evening, and just for fun, I'm curious how you might respond to this question. What do you consider to be the most compelling scientific evidence for God's existence and for a design and purpose in the universe? So if anybody can just shout out the answer, we'll just take a few people. Just curious, what would you say is the answer to that question?
Human mind.
Oh, that's a good one. Yeah. Anybody else?
I would say it's the Big Bang, because it's a creation out of nothing.
Yeah, good. Anybody else?
Life cycle of a cell.
Yeah, yeah. All great answers. Anybody else? One more maybe, if somebody is willing to.
Just the incredible fine tuning that we see in the universe.
Oh, thank you. Because that is the answer I was looking for. No, all of the answers are actually exceptional answers. And I think point out the fact that there's so much that we could point to in the universe and phenomena within the universe that really points to the reality of a creator. But one area that very much is the case, one scientific area that very much is the case is the anthropic principle. And of course, this is the idea that the fundamental constants and parameters and characteristics that define the universe are exquisitely fine-tuned in such a way that life is possible, and that if even one of these parameters or characteristics deviates in some instances imperceptibly from the values that they assume, life simply couldn't exist in the universe. And so you see this idea of design in the universe. You also see this idea of fitness for purpose in the universe. That is, the universe is just right, just the way it needs to be, so that life is possible. And so it's pointing to the reality of design in the universe, but also purpose in the universe. And one explanation for that, of course, is that there's a creator that is responsible for the universe itself. And I think many of you are probably familiar with, again, this idea of the anthropic principle, but also I'm sure you're familiar with some of the examples. So, the ratio of the electromagnetic and the gravitational force constants can't vary by more than 1 part in 10 to the 40th power. And, and the reason for that is because these two force constants play a role in star formation, and you get very different types of stars that would form if electromagnetism and the gravity, or if the electromagnetic force and the gravitational force were even slightly different. And of course, different types of star formation mean different types of chemical elements, with the idea that we wouldn't have the right suite of chemical elements that we would need for life to be possible. And perhaps the most extreme example would be the fine tuning that we see in the cosmological constant on the order of 1 part in 10 to the 120th power. And so again, these are familiar examples to many people, and these examples are not disputed, by the way. Most astronomers and astrophysicists readily accept the idea of the fine tuning of the universe. If there is a debate, it is really about what are the metaphysical implications of the universe's fine tuning. Now, interestingly enough, the idea of fine tuning, at least in cosmology, traces its origin back to the work of physicist Brandon Carter. Now, prior to Brandon Carter, there were some astronomers and physicists who identified what we would call anthropic coincidences. But Carter actually codified the idea of the anthropic principle, where he was taking part in a conference, in a symposium that was meant to celebrate an anniversary connected with Copernicus. And one of the outworkings of Copernicus's ideas is the Copernican principle, which is basically, in a nutshell, the idea that there's really nothing special about the Earth at all, that it doesn't hold any kind of privileged position in the universe. Again, there's nothing special about Earth. We're just one of millions and maybe billions of typical planets that could support life in the universe. There's nothing really special about Earth. And Carter actually challenged that idea as an atheist through a theoretical analysis where he essentially did a counterfactual analysis where he held all the constants of physics in varying except for one, which he allowed to vary. And then he theoretically determined the impact it would have on star formation and elemental production. And he concluded through his analysis that we actually live at the just right time in the just right location in the universe so that life could exist. And he called this at that time the weak anthropic principle. That concept today takes on a different meaning, but in Carter's system, the weak anthropic principle had to do with our time and location in the universe. Then he did something else where he showed that if the fundamental constants of physics took on different values, that life simply couldn't exist in the universe. And he called this the strong anthropic principle. And it was later on that Frank Tipler and John Barrow, in their book on the cosmological anthropic principle, redefined the concepts of the weak and the strong anthropic principle, where Carter, interestingly enough, as an atheist, interpreted the anthropic principle as being evident, self-evident. He argued that, well, of course, we have to be at the just right time and the just right location in a universe with the just right constants for life to exist. Because if we're in any other time or location in the universe, or if the constants of physics were any different, there wouldn't be observers to recognize that the universe wasn't fine-tuned for life. So he said, of course, that's the case. It was later on that Tipler and Barrow argued that there may actually be an explanation for the anthropic principle that argues that the universe itself is an imperative. There's something about the universe that is being dictated by something beyond the universe itself, so that the universe is the way that it is, so that life is possible. And this idea lends itself to the notion that there is a creator that ultimately is responsible for the universe itself. And so that's how, Carter and then later on Tipler and Barrow began to interpret the anthropic principle. But again, there's nothing controversial about the fine-tuning of the universe. Now, the question, of course, is does this fine tuning only manifest in the laws of physics and the fundamental constants of physics, or is there something? Do these anthropic coincidences extend beyond physics? Do they go into the arena of chemistry? Do we see them even manifested in biochemistry and biology? And the reason why that becomes an important question is because if indeed there's a theological explanation for the anthropic principle, if that the explanation is that there is a creator that is behind the universe, then you would expect that these anthropic coincidences wouldn't be just simply limited to physics, but they would manifest in chemistry, that they would manifest in biochemistry. And that's the purpose of the book, Fit for a Purpose, is to explore that question. And the idea that the anthropic principle extends beyond the constants of physics is not unique to me by any means, but it's an idea that I first began to entertain back in the late 1990s, the early 2000s, with a book published by Michael Denton, who also is a non-believer. He's an agnostic, called Nature's Destiny, where he argues that we see anthropic coincidences that manifest in chemistry and in biology. And in this book, he presents a number of examples of anthropic coincidences in these arenas, but it's really kind of a scattershot sampling of anthropic coincidences that at least open up the possibility that the anthropic principle actually, again, includes chemistry and biochemistry. And so what I do in Fit for a Purpose is I basically take on this question by looking at it systematically, analyzing chemical systems, and then systematically looking at biochemical systems to show that indeed we do see a very clear signature for the anthropic principle beyond the constants of physics. Now, one of the things that is important to recognize is that the way that we draw conclusions about the existence of the anthropic principle in chemistry and in biochemistry is different than how it's done in physics. Though conceptually you're making the same argument, the way you execute that conceptualization is very different. In physics, it is a counterfactual analysis. It's a theoretical analysis where, again, one of the constants of physics is allowed to vary while all the other constants of physics are held to be unchanging. And you, again, theoretically determine what would be the impact on star formation, galaxy formation, the production of chemical elements. And it is a quantitative characterization in physics, as you might imagine. But what you're doing is you are basically saying, number one, that the laws of physics or the constants of physics are endemic to the universe. They arise out of the very nature of the universe itself, and that these values are precisely what they need to be for life to be possible, and that there's no other alternative values that will work. So there's three criteria you're using that again, these laws of nature are again fundamentally specified by the very nature of the universe itself, that they are the just right values, and that there's no alternative universe that could account for the existence of life. When it comes to looking at that question in chemistry and biochemistry, what we're going to do is follow in the footsteps of somebody by the name of Lawrence Henderson, who in the early 1900s wrote a book called Fitness of the Environment, where Henderson, who also was a non-believer, was an atheist, argued that there appears to be these anthropic coincidences that we see in the very nature of chemistry. That is, the chemical environment of Earth has these just right properties that make life possible. Even though he ascribed to Darwinian evolution, he argued that if it wasn't for the fact that water has the just right properties, that CO2 has the just right properties, that organic compounds have the just right properties, that you would not have an environment for life to even exist. That is, he argued that there was a complementarity between the fitness of the organism for the environment and the fitness of the environment for life, where he argued that if the environment wasn't fit for life, it's not that you would have different types of organisms, you wouldn't have organisms whatsoever. And this idea really formed the foundation of the anthropic principle. And so it really wasn't Brandon Carter who really first codified the anthropic principle. It was actually Lawrence Henderson. But interestingly enough, his ideas were simply ignored by many people in the scientific community, in large measure because what Henderson was doing was introducing or reintroducing teleology back into biology. Darwin's revolution was in part responsible for removing teleology from biology, where it was just mechanism alone that explained the nature of biology. And what Henderson was doing was saying that there actually is a teleological element to biology. And for that reason, people largely ignored his ideas until almost a century later, where you see Denton building off the ideas in his book, Nature's Destiny, building off the ideas of Lawrence Henderson. And so in my book, I'm doing the same thing, where I'm building off of Denton's ideas, who in turn is building off of Henderson's ideas. But it's Henderson's approach in that book that I've used in Fit for a Purpose. And let me illustrate how that works by taking a look at an example of where we see anthropic coincidences in chemical systems. And this would have to do with carbon, with the carbon atom. The carbon atom is a really unusual material that has the just right set of properties that make life possible. And there really are not any other alternatives to carbon that could support living systems. And this was a point that Henderson made in his book Fitness of the Environment. And this is remarkable because Henderson drew this conclusion before we actually had a theory for chemical bonding. And quantum mechanics hadn't really been introduced into chemistry by this point in time. And today we do have a modern day understanding of chemical bonding. And in light of that modern understanding, Henderson's insights hold up. And so he was incredibly prescient in his identification of these anthropic coincidences. But again, carbon is a really unusual chemical element. And carbon has an incredibly rich chemistry that makes the chemical complexity for life possible. And to just highlight the uniqueness of carbon, for those of you that know anything about how the different areas of chemistry are divided, you'll know that there are two major divisions in chemistry: inorganic chemistry and organic chemistry. Organic chemistry is a division that focuses on the chemistry of carbon atoms or molecules made up of carbon. And inorganic chemistry is the chemistry of the remaining periodic table, remaining elements on the periodic table. And what this is highlighting is that the chemistry of carbon is so unusual, and that unusual nature produces such a rich chemistry that in and of itself, it is beyond the capacity of one person to fully master the chemistry of carbon compounds. And carbon uniquely is able to form multiple chemical bonds, and those chemical bonds can be single bonds, double bonds, triple bonds. Carbon can form linear chains, rings, branched chains, branched rings, and rings that have a unique type of chemical bonding called aromaticity. Carbon can form stable bonds with what are called heteroatoms: hydrogen, nitrogen, oxygen, sulfur, phosphorus, the halides. And these are all characteristics that make carbon a very important framework. In fact, the only framework for producing a chemical system that, again, would allow for life to be possible. And so, in other words, carbon is this highly unusual material that has the just right properties for life, and its properties that are so unusual arise out of the very laws of nature itself. They are prescribed by the laws of nature itself, right? It's not a contingent outworking. It's an outworking that is constrained and prescribed by the laws of nature. Now, is carbon unique? Well, the way to answer that question is to look at a periodic table and note that chemical elements in a periodic table that are in the same row, in the same column, have essentially very similar chemical and physical properties. And so the element that is right beneath carbon on the periodic table is silicon. And of course, there is the claim on the part of many people that silicon could actually be used to build living systems, that you could have silicon-based life. This is an idea that is remarkably present today in astrobiology. But the fact of the matter is, a good course in inorganic chemistry will demonstrate to you once and for all that there's no way that life could be silicon-based. Silicon-silicon bonds are incredibly weak. Silicon is a highly reactive element. Silicon is susceptible to oxidation. And when the silicon dioxide forms, it's a solid material versus carbon dioxide, which is a gaseous material. And it's soluble in water as well as in air. And this is a huge difference in silicon and oxygen that I'm not going to get into, but is one of the most important reasons why silicon isn't a suitable framework for life. Silicon hydrogen bonds are very weak, and silicon cannot form stable chains and rings and compounds like that. So in other words, we can show empirically that carbon is a unique material. And so this is a qualitative analysis that we're doing. It's not a quantitative analysis, but it's, I would argue, more robust than characterizing the anthropic principle in cosmology, because it is experimentally based. So everything I'm going to show you now, when it comes to the anthropic coincidences that we see in biochemistry, are experimentally demonstratable. These are not theoretical. This is not a theoretical assessment, but an experimental assessment. I'm going to skip this just because of time's sake, and just simply say that, again, we can show that again, when we look at chemical systems in a very similar vein to what Henderson did, that we live in a chemical environment, or that the universe has a chemical environment that is ideally suited for life, that water is a highly unusual material that has the just right properties for life. There are no alternatives for water as a solvent system for life, that again, carbon is a just right molecule to build the complexity we need to support biochemical systems, to support living systems, and that carbon dioxide and oxygen, for example, have just right properties that make life possible. Now, the question is, does the anthropic principle extend into biochemistry? And in the book, I argue that the answer is yes. And again, the criteria that I'm using is this: are biochemical systems specified by the laws of physics and chemistry? Are they prescribed by the laws of chemistry and physics? Or do they arise through the outworkings of historically contingent evolutionary processes? The second criteria is, are the properties that biochemical systems assume precisely those needed for life, and are there any alternatives? And if these three criteria are met, then you could argue that the anthropic principle is manifest in biochemical systems. Because this, again, is exactly the criteria we're using in cosmology. The constants of physics are prescribed by the very nature of the universe. They are precisely the values that you need for life to be possible. That is, there's a fitness for purpose to the universe, and that there's not alternative values, or there's not really an alternative universe that could actually support life. So it's the same set of criteria. Okay, so in my book, I take a look at these criteria for proteins, nucleic acids, phospholipids, which are the components that make up cell membranes, for key metabolic processes, protein synthesis, DNA replication, and then energy production pathways. Now, the reason I chose these is because these are the core biochemical systems. That if you're going to see the anthropic principle, it's going to be in these particular systems. These are the core biochemical systems for life. And these are also the systems that you need for a minimal cell. That is, if you don't have these systems in place, that protocellular entity cannot be considered to be a bona fide life form. So these are the minimal systems that you need for life to exist. This is what a minimal cell needs, and these are also the core biochemical systems. So if you're going to see the anthropic principle, it should be manifested in these systems, and it should be consistently manifested in these systems. And the short answer is that indeed we see these three criteria being satisfied for these systems. And what I want to do is illustrate this by taking a look at proteins as an example. And the reason why I want to focus on proteins was articulated by Michael Denton, who in a essay in a book called The Fitness of the Cosmos for Life, he writes, if the cosmos is uniquely fit for life as it exists on Earth, then given their primal significance, the protein should be another uniquely fit ensemble of natural forms. In other words, if you're going to see the anthropic principle, it's going to be in proteins. And so what we're going to argue is that proteins are the structure of proteins, the properties of proteins are not the outworking of a historically contingent evolutionary history, but are fundamentally prescribed and constrained and dictated by the laws of nature, that they have exactly the properties you need for life, and that proteins are unique in the role that they play in living systems, that there's not alternatives that could be used for proteins. Okay, so here is a cartoon showing the structure of proteins. And I think probably many of you are familiar with diagrams like this. When we think about proteins, we think about four levels of structure. There is the primary structure or the primary sequence of proteins. This is the sequence of amino acids that are used to build proteins. And there are 20 different amino acids to first approximation that are used to build proteins that can be sequenced in a near infinite number of ways, where the precise amino acid sequence dictates the way that the protein chains fold, and that determines the protein's function. And the primary structure is, again, the sequence of amino acids that are used to build the protein chain. The secondary structure is the conformation of the protein backbone, and the protein can adopt these regular conformational patterns that produce structures like an alpha helix or a beta pleated sheet. And then the chain, as it adopts these secondary structures, will interact with itself in three-dimensional space to form the tertiary structure of proteins. And then individual folded protein chains can interact with others to form protein complexes. So this is primary, secondary, tertiary, and quaternary structures to proteins. And it turns out that even the simplest cell requires probably requires well over 1,000 different types of protein molecules to carry out all the different operations that are needed for life to exist. Okay, so here are the 20 amino acids that are used to build proteins. And we'll dissect the structure of amino acids in here in a second. But what we see with amino acids is essentially a structure where you have a carbon atom, and then bound to that carbon atom is a carboxylic acid functional group and an amino functional group, a hydrogen atom, and then another group that is called an R group. And that R group determines the identity of the amino acid. And there are 20 different R groups that are used to build proteins. And those R groups vary in terms of size, in terms of hydrophilicity or hydrophobicity, that is, in terms of their capacity to interact with with water. Some of them vary in terms of their chemical properties. Others vary in terms of charge. And so you see an ensemble of R groups that are essentially giving unique properties to each of the amino acids and are playing a role in establishing the protein structure and function. And the way in which the primary structure of proteins is formed is through what chemists call a condensation reaction, where the carboxylic acid moiety of one amino acid reacts with the amino group of another amino acid. And as a result, the element of, or it's not the element, but the a water molecule is removed collectively from these two molecules, and a chemical bond is formed between them. And that chemical bond is referred to as a peptide bond. It's also known as an amide linkage. And so this bonding is repeated along the length of the amino acid chain to build a protein. And so each of the amino acids in that protein chain is linked together through, again, a peptide bond or an amide linkage. Now, as it turns out, let me go back. As it turns out, this amide bond is a really unusual chemical bond. It has a really unusual set of properties. And as we'll see in a minute, those are the just right properties you need for life to be possible, and that there's not really an alternative to the amide bond that can exist to form macromolecules that could assume the properties, the functional properties of proteins. And so, for example, let me unpack this. Are there alternatives to again, an amide linkage, or to a polyamide, or to a polypeptide? And the short answer is there doesn't appear to be. And the closest analog that we have to proteins would be polyesters formed from alpha hydroxy acids. Now, I think probably most of you are familiar with the famous Miller-Urey experiment, right? Where Stanley Miller in the 1950s filled up a glass apparatus with constructed a glass apparatus that was supposed to simulate the conditions of the early Earth. And he had a flask of boiling water, right? He was very careful to evacuate the apparatus ahead of time, so there was no oxygen in it. And then he introduced ammonia and methane and hydrogen gas into the headspace, and through this electrical discharge was able to produce amino acids, at least some amino acids. And this was considered to be a very important experiment that validated the O'Parent-Haldane hypothesis, because he showed that you could generate the building blocks of proteins under the simulated conditions of the early Earth. In his experiment, however, he formed not only amino acids, he formed other organic materials, including alpha hydroxy acids. And in fact, alpha hydroxy acids occur at a much higher level than amino acids in his experimental design. And so in terms of prebiotic availability, you would actually argue that life really should have been built around polyesters formed from alpha hydroxy acids, not from amino acids. Not from amino acids because of, again, prebiotic availability. But as it turns, and again, here's showing the chemical similarities between ester linkages and amide linkages, between polyesters and polyamides. Polyester can be formed with a carboxylic acid reacting with an alcohol, which is what an alpha hydroxy acid is. The hydroxy is the alcohol moiety. An amide can form with the reaction of a carboxylic acid with an amine. And so these are very similar chemical reactions that are condensation reactions that produce, in principle, very similar compounds. The difference, however, is, and sorry, getting ahead of myself. Here's a chemical reaction showing in the upper left-hand corner lactic acid. Lactic acid would be the alpha hydroxy analog to the amino acid alanine. And you can form, if you take alanine and react it with itself, you can form a polyalanine, which would be a protein where there's only a single amino acid residue, alanine. Likewise, you can form polylactic acid through a very similar type of reaction, a condensation reaction where you're forming a polyester, a molecule called a polyester. The problem is that the polyester bond is very different than the ester linkage is very different than the amide linkage or the peptide bond. Even though superficially they look like they're essentially the same kind of bonds, their chemistry is radically different. Polyesters have single bond character, whereas polyamides have double bond character. And this is really, really important. And so the way to think about this is, imagine you had two boards where each of those boards would be analogs to to atoms. And that the nail that you use to drive between the two boards to hold them together would be the chemical bond, right? And so if you have a single nail through those two boards, they can rotate relative to one another, right? If you drive another nail between the two boards, you now have a situation where the boards cannot rotate relative to one another. And that double bond character is really very important. And that double bond character arises out of a phenomenon known as resonance that is due to the difference in electronegativities between nitrogen and oxygen. And those electronegativity differences introduce double bond character into the amide linkage through a phenomena called resonance, where with polyesters, you don't get that kind of that type of resonance taking place. And this double bond character, first of all, makes proteins much less susceptible to hydrolysis than polyesters. And this, of course, is very important because once you form that protein, you don't want it to break down in an aqueous environment. And so the double bond character of an amide linkage compared to an ester linkage actually gives chemical stability to proteins. Also, the amide, because the amide linkage has double bond character, it actually is rigid and it's planar in its geometry. And that rigidity actually allows for protein chains to form these complex three-dimensional structures that are stable. A polyester or an ester linkage with single bond character is too floppy for that polyester to form stable three-dimensional structures. The double bond character also allows for what's called a transgeometry. So when we look at again the double bond character of an amide, what that does is it actually creates two alternative configurations for the atoms in an amide bond. In one configuration, you can have a carbonyl from the carboxylic acid and the hydrogen bound to the nitrogen on the same side of the double bond. That's called a cis geometry, or on the opposite side, that's called a trans geometry. Well, it turns out that the nature of the amide linkage is such that the most stable configuration is the trans geometry. And it turns out that this is really very lucky, because if it was, if either geometry was equal in energy, equal in terms of energetics, or if the cis was favored over the trans, you couldn't get secondary structures to form in proteins. The trans geometry in an amide linkage allows for hydrogen bonding interactions to stabilize the alpha helix or the beta pleated sheet structures. That trans geometry also creates what are called steric effects that allow for the folding of the protein chain in such a way that only alpha helices and beta pleated sheets can form. And so in other words, what we see is that the amide bond is a very unusual bond that has double bond character. And that double bond character arises from from the electronegativity differences between the nitrogen and the oxygen atom. And that electronegativity difference, again, creates resonance, which allows for double bond formation or double bond character that then creates rigidity to the backbone that allows the protein to form stable three-dimensional structures. It forces a trans geometry that gives you the right orientation of atoms in space to stabilize these secondary structures. It forces psi and phi bond angles such that the only structures that are permitted are alpha helice and beta pleated sheet structures. And it imparts chemical durability to the protein backbone. And this is what Banvanar and Martin say. These are two biophysicists that are marveling at the unique nature of the amide bond and the anthropic coincidences that emerge. And they say this: one cannot but marvel at how several factors, the steric interactions, hydrogen bonds, which provide the scaffolding for protein structures, the constraints placed by quantum chemistry on the relative lengths of hydrogen bonds and covalent bonds, the near planarity of the peptide bond, the key role played by water, all reinforce and conspire with one another to place proteins in this novel phase of matter. And so in other words, when we look at the secondary structure of proteins that arises out of the amide linkage that is responsible for joining amino acids together, we see that this amide bond is arising out of, is prescribed by the laws of nature, has the just right properties for life to be possible, and there doesn't seem to be an alternative that will work. The closest analog would be, again, an ester linkage, and the ester linkage is radically different than the amide linkage. Now, let's move to beyond secondary structure to tertiary structure. And one way we can describe the tertiary structure of proteins is through this concept of folding. That is, once you have the secondary structures in place, those secondary structures will interact with each other to form the three-dimensional structure or the tertiary structure of proteins. And what we see here is, again, evidence for the anthropic principle. We see these anthropic coincidences. So, for example, to appreciate this, we need to think a little bit about a concept called protein space. Protein space is basically what are the possible structures that could exist for proteins, right? What are the possible structures? And so for a protein that is 150 amino acids in length, which is a relatively small protein, by the way, you would have 20 to the 150th power possible amino acid sequences, right? 20 to the 150th power. That's a huge, huge number. But it turns out that it's not the primary sequence that we're all that interested in. It's the three-dimensional structure of proteins. And it turns out that for a protein that is 150 amino acids in length, there are at minimum 10 to the 68 ways that protein chain can fold, which means protein space when we think about proteins as three-dimensional systems is 20 to the 150th power, that whole quantity to the 68th power. That's just for proteins that are 150 amino acids in length. That is an incredibly vast space of protein, possible protein structures. Well, it turns out that there's only a few thousand ways that protein chains can actually fold. When we look at proteins in nature, we discover basically the same folds that recur over and over again. And there's somewhere between 1,000 to 4,000 folds that have been identified. Now, this is remarkable because, again, there are for, again, an amino acid, sorry, check that, for a protein that's made up of 150 amino acids, there are 10 to the 68 ways that that chain can fold. And what we're looking at in nature is only 10 to the third ways, that 10 to the third folds that we've identified. And that means, and we've also discovered that not only are these folds, again, the only folds that we see, but each fold is able to perform a wide range of functionality. The folds are designed in such a way that they can carry out a wide range of different types of functions, and different amino acid sequences will actually yield the same fold. And so it's not a unique fold for each unique amino acid sequence, but different amino acid sequences can give you the same fold. And this implies that there are these physical chemical constraints that are essentially dictating the way that protein chains can fold. And this is not surprising because biochemists have discovered that, for example, when alpha helices interact, they can only interact in very specific ways. When alpha helices interact with beta pleated sheets, they can only interact in very specific ways. There was a very famous protein chemist by the name of Kothia who wrote this decades ago now. Helices and sheets packed together in one of a small number of ways. The connections between secondary structures obey a set of topological rules. In other words, that there are these constraints that arise out of topology that dictate the way that secondary structures interact and in turn determine the type of folds. So in other words, the folds that we see in proteins are not historically contingent, but are actually prescribed and constrained by the laws of nature, and they have the just right properties that make again, life possible. And so you see these anthropic coincidences. There's another way that we can get at the same insight, and that's through a kind of a thought experiment that was done by Banvanar and Martin, which are two biophysicists. And I quoted them earlier. And what they did is they said, imagine that you have a tube, and that tube is formed from discs that are tethered together, where the discs would be analogs to amino acids, and the tether would be the chemical bond between the amino acids. And he said, imagine that we have a set of 20 discs where the discs have different hydrophobicities. That is, they interact with water either by being attracted to water or being repelled by water, and that these flexible tubes that result will interact with each other in such a way to form stable interactions, and also in such a way to exclude water from the interior of the fold. So the tubes are going to fold back on themselves into compacted structures designed to expel water from the interior. And so they then develop something they called a folding parameter, which they defined as the ratio of the tube diameter to the range of attractive interactions. So the way to think about the folding parameter is that if the tube is really fat, then the folding parameter is going to be very, very large, meaning that the diameter is very large relative to the range or the spacings of the interaction of the tube with itself. And so, in other words, the tube can't fold if the folding parameter is very large. If it's very, very small, like a string, there's an infinite number of ways that the tube can fold. But if the folding parameter is about 1, you wind up with about 1,000 folds that can exist, and those 1,000 folds essentially represent a balance between steric interactions chemical attractions, physical chemical attractions and steric repulsion, right? And it turns out that the folds that they determined are exactly the same folds that you see in proteins that are found in nature. That is, it looks as if it's the chain geometry and the hydrophobicity profile that actually is dictating the folding parameters of proteins. And it turns out that the folding parameter for the proteins found in nature is 1, right? So it's in this sweet spot. And so this is remarkable that the geometry of the protein chain is exactly the diameter it needs to be, and the range of interactions between the chemical groups of proteins is such that you get this folding parameter that gives you, again, that leads to the formation of the just right folds. And so this means that proteins actually are essentially a critical phase. They are this transitional point in terms of their three-dimensional structure. And this means that proteins can only fold, and again, in a limited number of ways. And this actually resolves something known as the Leventhal paradox, which is that the number of possible ways that a protein chain can fold is so vast that there's no way that protein chains could explore all the possible configurations to arrive at the native state structure, the minimum energy structure, given the duration of the universe. That even if the proteins could fold every picosecond, there's not enough time for a single protein chain to fold, yet protein chains will fold just like that within milliseconds. And the way to explain this is that there's only certain folds that are actually possible, meaning that proteins can very quickly essentially explore the space available to it to find that native state structure, that minimum energy structure. This also means, because you're at this transitional point, that proteins have conformational flexibility that is needed for proteins to function as enzymatic catalysts and receptors. It also means that proteins are robust to mutations, that if you alter the amino acid sequence of proteins, it means that they're more likely to essentially retain that folded geometry and therefore retain their structure, their function, and that a single protein fold can actually perform a wide range of functionality by varying the amino acid composition of that fold. And so this is what Banvanar and Martin write. They say the common belief is that given a sequence of amino acids with all the attendant details of the side chains and the surrounding water, one obtains a funnel-like landscape with the minimum corresponding to its native state structure. Each protein is characterized by its own landscape. In this scenario, the protein sequence is all important, and the protein folding problem needs to be attacked on a protein-by-protein basis. Protein folds do not evolve, however. Rather, the menu of possible folds is determined by physical law. In that sense, is that if evolution acts in the theater of life and shapes sequences and functionalities, but does so within the fixed backdrop of Platonic folds. And so, in other words, what we're looking at with proteins is that the folds that are, again, dictated fundamentally by the laws of nature. They're prescribed by the laws of nature. They're the just right folds that you need for life to be possible, where you have, again, the just right folding parameter, the just right conformational flexibility, the just right number of folds that allow proteins to adopt their structures. They go on to say, in contrast, our model calculations show that the large number of common globular protein folds reflect the deeper underlying unity in their behavior. This landscape is pre-sculpted by general considerations of geometry and symmetry. Also, we note that when we continue looking at protein tertiary structure, that proteins have these cavities and crevices on their surface that are critical to the function of the protein. This is where small molecules bind. This is where proteins will interact with other proteins. And it turns out that there's a limited number of possible protein binding sites that could exist on proteins. For about 400 binding sites for small molecules and about 1,000 sites for protein-protein interactions. And so in other words, these active sites on the surface of proteins are, again, appear to be prescribed by the laws of nature and are precisely what you need for life to be possible. And again, what you see here is Gao and Sklonik, who discovered this, say the coincidence of structurally similar pockets and structurally similar proteins with similar patterns of residue conservation cannot in and of itself be used to infer evolutionary relationships between proteins. And again, the idea here is that proteins are not evolving, but they are the structures that we see isn't the outworking of evolution. It's again prescribed by the laws of nature. And then last but not least is the question, why the particular 20 amino acids that we see that are used to build proteins. And it turns out that there's a deep-seated rationale for this set of 20 amino acids. And this is interesting because there's close to 500 amino acids that could be used in principle to build proteins. And what we see is that really only 20 amino acids are suitable ultimately out of all the possibilities to build proteins. As we mentioned, you can't have alpha hydroxy acids, you have to have alpha amino acids. You could, in principle, build proteins from diacids and diamines. The problem here is that you have introduced an unnecessary level of chemical complexity into the system. Amino acids are the simplest molecules that can be used to build proteins. If you had diacids and diamines, you'd have to have a canonical set of 40, where you would have to have a diacid and a diamine that had identical R groups in order to build protein chains. You have to have alpha amino acids. You can't have beta, gamma, delta, or N-alkyl amino acids because none of these will form secondary structures. You have to have a hydrogen in the alpha position. You can't have any other chemical group because of steric effects. And when we look at the R groups that we see on proteins, it turns out that this is the just right set of R groups that with respect to size, charge, and hydrophobicity. Stephen Freeland and his collaborators who discovered this said, the amino acids found in proteins form a highly unusual set of 20 amino acids. A maximum of 0.03% random sets outperformed the standard amino acid alphabet in 2 properties, while no single random set exhibited greater coverage in all 3 properties. The set of R groups is unique and is just right, the just right set of R groups. So in other words, what we've shown with proteins is that the structure of proteins seems to be fundamentally prescribed by the laws of nature. And these laws of nature produce, again, these just right amino acids that are joined together by a just right chemical bond that then results in the just right formation of secondary structures and consequently tertiary structures that are just right for proteins to be possible. And I could continue talking about the fact that we even see anthropic coincidences when we talk about protein quaternary structure, but I'm going to go ahead and stop there because I realize that this has been a fairly technical description. But the point is that we actually do see evidence for the anthropic principle in biochemistry. We see it in chemistry, we see it in physics. And if we really envision a universe that is the product of a creator, then we would expect that these anthropic coincidences would manifest in matter, in living systems at every level, whether it's at the level of the fundamental constants of nature, the chemical properties of molecules, or in the chemical and physical properties of biomolecules. Okay, I'm going to go ahead and stop there and open up the floor for you to ask any kind of questions. You can raise your hand and ask a question. You can just shout out your question, or if you'd like to type your question in the chat, you can do that as well. And I note that Don sent me a message right when I logged in that he's really enjoying being the instructor for the advanced seminar on biochemical design. And Don, I'm grateful that you're doing that. You're a perfect choice for that job. And yeah, so thank you for doing that. I'm glad that you're doing that.
Thanks, Fuzz. Maybe I could just kick off with a question. The slide, Fuzz, early on in your presentation where you talked about the key biochemical molecules that you are highlighting in your book, proteins, phospholipids, et cetera, et cetera. I noticed that carbohydrates were absent. Was that an oversight on the slide, or is that?
No, it's not an oversight. I intentionally omitted carbohydrates in part because I was not able to find any kind of work where people were asking questions about carbohydrates in the same way that they were asking questions about proteins or nucleic acids or even phospholipids. And I think part of it is the sheer complexity of carbohydrate biochemistry. However, I do have a discussion of glucose in the section where I deal with the glycolytic pathway. And I talk about the fact that glucose is the just right carbohydrate. It's actually the just right molecule to be used as a energy, as a fuel molecule, as an energy producing molecule for biochemical systems. So we do touch upon carbohydrates, but kind of in an ancillary way in the book. Part of the issue is, again, carbohydrate biochemistry is very complex, and to me, this is one of the areas. And there's quite a bit that we understand about carbohydrate biochemistry, don't get me wrong, but this is an area where we are really just beginning to understand the structure function relationships of carbohydrates. Because, with a lot of proteins and even lipids have oligosaccharides that are bound to them, and those oligosaccharides are functioning as information harboring systems. Mm. They harbor a chain of oligosaccharides contains exponentially more information than a corresponding chain of amino acids. So if you have a oligosaccharide that has 5 sugar residues in it, I don't know off the top of my head, I'd have to on a piece of paper do the calculations, but you're dealing with almost an order of magnitude more information than maybe a couple of orders of more information than if you had a polypeptide of 5 amino acids in length. And so we're just beginning to understand some of those structure function rules. So I think our understanding in biochemistry is still, with regard to carbohydrate biochemistry, still enough in its infancy that it's hard to really ask these kind of questions that you would need to ask, for the anthropic, to determine if the anthropic principle applies to biochemistry. But all this to say is that what I did in the book is really a preliminary study, right? There's so many other systems that could be explored. But if the question is, does the anthropic principle even exist in biochemistry? You want to go to the core systems that have been studied sufficiently that you can actually ask and answer those questions. Yeah.
Thanks.
Buzz, at the beginning of your talk, you mentioned teleology. Can you refresh everybody's, what exactly is that and how does it apply to what you're saying?
Yeah, that's, and thank you. I'm sorry I didn't define that. Teleology is the idea that there is design and purpose in a system. And so, prior to Darwin, when people looked at biological systems, they saw a purpose to the design. They saw a teleology to the design, that there was that the designs were real designs that were constructed in such a way to be purposeful. And Darwin comes along and he adopts an anti-teleological view where he's arguing that biological systems aren't fundamentally dictated by a cause, a mind, but rather it's mechanism alone that explains them. And as a result of that, there really isn't a ultimate purpose to biological systems. These are the outworkings of a historically contingent, random evolutionary process. And what is produced is just happenstance. Interestingly enough, biologists will use a term called teleonomy, where they would argue that the appearance of design that we see in biological systems is produced by the blind watchmaker of evolution, and it's apparent design. It's not actual design. And so when you start talking about the anthropic principle, you're reintroducing teleology back into science. And so in cosmology, this was done in the 1970s, where you see physicists debate the question of teleology, where there does seem to be something that is undergirding the universe, that there's an intentionality or a purpose that undergirds the universe. And Henderson was bringing back teleology as well, where he was arguing that all of these properties that we see for water and CO2 and oxygen and organic compounds have to be more than just a coincidence. That it's something beyond a coincidence, that there is some kind of purpose or an intentionality in the construction of the universe in such a way that it makes life possible. And so, yet he was an atheist, and he was trying to sidestep the theistic implications of what he was saying, but he very much was arguing for a teleology, and he saw a metaphysical significance. So he followed up his book, Fitness of the Environment, with a book called The Order of Nature, which is really a philosophical work about reintroducing teleology back into science. But for an evolutionary biologist to say that there is design and purpose is horrifying, right? If anything characterizes modern day biology, it's a very strong anti-teleological mindset. And yet what we see now here we're dealing with biochemistry, so we're dealing with the origin of life question, But, to me, even if you adopt an evolutionary view for the origin of life, you cannot escape the necessity of a creator, because what this anthropic principle is telling us in biochemistry is, even if you say life evolved through chemical evolution, what you're saying is that the endpoints of that evolutionary process seem to be rigged at the beginning of the universe, that everything has been jimmy rigged at the get-go, so that evolution is inevitably going to lead you to exactly the biochemical systems that you see. So whether you see the origin of life is the direct work of a creator, which is still would be my preference, or the outworkings of evolution, you can't escape the teleology. It looks as if somebody has purposed this. And since I've written the book, I'm now going back and looking at prebiotic chemistry. And you are beginning to see these really interesting anthropic coincidences that seem to be latent in prebiotic chemistry. In other words, the reactions that people have identified in the lab that could conceivably contribute to chemical evolution are operating in such a way that you wind up producing, again, the just right materials that you need for life to be possible. So for example, I wrote a blog article about the Krebs cycle, and there's also a discussion of the Krebs cycle in the book. But the Krebs cycle is the hub of intermediary metabolism. It's this cyclical pathway that not only is playing a key role in generating high energy electrons that can be used to generate ATP, but the intermediates in the Krebs cycle can be siphoned off and form the beginning points of a number of different other metabolic pathways that are producing building block materials that are needed for other biomolecules and other biochemical systems. And it turns out that those intermediates that are in the Krebs cycle had this really unusual set of properties that make them ideally suited to serve as intermediates. But they also are molecules that seem to be unusual in that they are going to form under conditions on prebiotic Earth, and they're part of a very small subset of organic materials that have these just right set of properties that make them conducive to appearing on the early Earth. And so it's really eerie to think that the molecules that form the Krebs cycle with a just right set of properties are also the very molecules that have the properties that lend themselves to being formed under the conditions of the early Earth. And so it's almost as if the laws of nature and the geochemical constraints of the early Earth have been, or that somebody conspired to make all of these things line up in such a way that the molecules you need for intermediary metabolism, for the core of intermediary metabolism, naturally form. And that, there's 10 million organic molecules in Biostein, and there's probably about 100 molecules that actually have those properties that make them, that lend themselves to forming under the conditions of the early Earth. And of that set, you see all the Krebs cycle intermediates that form, or that the intermediates that are part of the glycolytic pathway naturally form. If you put one of the intermediates in the glycolytic pathway in water under conditions that could conceivably exist under the early Earth, the other components will begin to form. And so you naturally form the intermediates of the glycolytic pathway, just like you naturally form the intermediates. And again, when you look at the glycolytic pathway, it's a just right, the structure is a just right structure. There's not alternative pathways that could take the place of glycolysis. There's not alternative pathways that could take the place of the Krebs cycle. And the intermediates are these just right intermediates that have the just right properties. And so you see all these really eerie anthropic coincidences that are beginning to emerge in prebiotic chemistry.
So teleology then is similar to, let's say you're looking at the inside of your car engine and you're trying to figure out, why did the engineer put that there? What's the purpose of this part? So the same way a biologist could look at a cell and say, what's the purpose of this molecular machine inside the cell?
Yeah, and well, and that's the implications of teleology, but you're bringing up a really interesting point, because when we look at an automobile engine, and I'm not very mechanically inclined, and so when I look at an automobile engine, there's probably parts there that it's not evident, it's not self-evident to me, why that particular part is there, let alone why it's actually designed to look the way that it looks. But because I know that automobile engine is designed, I know that there's got to be a reason, right? And so I'll ask the why question, and the why question is intimately connected to the belief in teleology, right? That why would the engineer do that? And I'm expecting an answer that makes sense, right? It's just that I don't understand enough as a novice to know what that is, immediately. But if you adopt an anti-teleological view, then you would say, well, that automobile engine was the product of a historically contingent evolutionary process. It's just happenstance. Why is that part the way it is? That's what evolution did, right? It evolved it to be that way. There's no real rhyme or reason, right? Don't even bother asking the why question. That's just the way it is, right? And by the way, we know it must have evolved that way because here's another engine with the same kind of part. And so clearly there was an engine that was the evolutionary ancestor of these two engines that had that part. And this is just retained as part of that evolutionary history, right? That's totally absurd. But yet when we look at the cell and we see the machinery in the cell, that's exactly how biologists interpret it. That design is just apparent design. There's no rationale for it. Why are proteins the way they are? Well, it's just the way it is, right? This is just the outworking of, the transition from the RNA world to the DNA protein world. And it just has happened. Protein just happened to be what nature settled upon. And it's, there's not really a reason. But yet when you ask the why question, which again is deeply connected to the issue of teleology, there's an explanation, right, for why proteins are the way they are, and that explanation leads you to these anthropic coincidences. Yeah, so really, really important point that you're bringing up. It's a completely different mindset. Yes.
I recall that those early experiments. Paul. Oh, yeah, thanks. Those early experiments by Urey and Miller, they had equal numbers of left-handed and right-handed amino acids, but life as we know has only one left-handedness, I believe.
Yeah.
Is that still a mystery? Or have they tried to have any explanations come up with?
There's a whole ensemble of explanations that people have proposed for how you could gain chiral enrichment, but most of the explanations lack relevance to the conditions of the early Earth, or they don't give you 100% chiral enrichment. So yeah, there's a lot of ideas, but there's a difference between people having a lot of ideas and an idea actually providing real explanatory power, right? So a lot of ideas, but there's no real explanation for how homochirality emerged. Yeah, there's a lot of issues with the Miller-Urey experiment, to be certain. There's a lot of issues, with that experiment.
Just go ahead, George.
finally unmute. There we go. A lot of this stuff is certainly way beyond me, but it makes me hungry to learn more. Do I understand the anthropic principle that you're explaining to be the equivalent of like you talked about the proteins being constrained to 10 to the 3 number of folds? Is that the same as thinking as a constant in the cosmic anthropic principle, like, you know, the weak nuclear force or something like that? Is that a right way to think about it? That 10 to the 3 represents one of the constants of biology?
Well, yeah, the 10 to that 10 to the 3 folds is really evident that that there's a physical chemical forces that arise out of the nature of the universe itself that are prescribing the folds that we see. If there is a constant or a parameter that would be akin to the parameters in physics, it would be the folding parameter that Banvanar and Martin identified, which would be the ratio of, again, the diameter of the protein chain to the range of the, you know, chain interactions. So that folding parameter would be akin. In some instances in biochemistry, you can't really, you know, say that there's a constant or something analogous to a constant. You can't really say that. But you can show, again, that the way things are is just right, and that there's no alternatives by comparing the most reasonable and closest chemical system to the system that you see in biochemistry. So it's, you know, in some instances you have parameters that could be used. Other instances, not so much. But conceptually, it's the same argument.
Is it
Right.
more like the Goldilocks zone then, rather than a constant?
Well, the thing is, when you think about the anthropic principle in cosmology, and I understand why this is, everybody gets hung up on the fine tuning of the constants, right? And in the extreme values of the fine tuning. And that fine tuning definitely suggests design, but really the anthropic principle is about the idea that the universe displays fitness for purpose. That is exactly the way that it needs to be so that life is possible, and that it can't be any other way. And the way that you show that it can't be any other way is by demonstrating that the constants are fine-tuned, right? Which involves varying one of the constants while all the other constants are left unchanged. And then you can show that no other value for those constants really work. So likewise, in biochemistry, what you're saying is that there's a fitness for purpose, that biochemical systems are exactly the way they need to be, and they can't be any other way. And the way you show it there is by trying out different chemical systems that could, in principle, have existed on Earth instead of the ones that we see. And you can show that none of those systems actually work. So with proteins, they're polyamides, right? They're macromolecules that are called polyamides. And the closest analog would be, again, a polyester. And you can show that polyesters don't work, whereas polyamides do, if they're made out of amino acids with a just right set of properties, right? So it's a qualitative comparison. So there's no constants that you're dealing with, but it's an experimental comparison. So I can do the experiment and I can show you that polyesters won't work, right? You know, and so you can experimentally, you know, address that question. But you do from time to time see these constants or these parameters that are fine-tuned as well. So the folding parameter has to be fine-tuned to approximately the value of 1. If it deviates, right? With another plate, like with water, you can show the anomalous properties of water that make it just right for life to be possible arise out of the hydrogen bonding interactions. And so you can go in and the strength of the hydrogen bond becomes a physical parameter that you can vary and show that if the hydrogen bonds were any stronger or weaker, water wouldn't work as a solvent system for life. It has the just right set of properties. When it comes to the formation of cell membranes, phospholipids have something called a packing parameter that has to assume a very precise value for membranes to form. So there are places where you can quantify things, but it really ultimately is a qualitative comparison. But I think it's what you lose in quantitation, you gain in experimental robustness, if that makes any sense, George.
Is that why you talked about the silicon-based
Yes.
system that
Yeah.
just wouldn't work? Because,
Yeah, that's the way you're showing that. So not only are you saying, well, carbon has these unusual set of properties that are just right for life, and those properties arise out of the laws of nature, but we can show that nothing else works.
Right.
Right. So that, and we can do the experiments, and people have, right? So it's an experimentally based conclusion. I would encourage you to get the book Fit for a Purpose. Because in the way to read that book, if you're not, you need to know a little bit about biochemistry to really appreciate the book. But the way to read the book is to read the introduction in the last chapter, and you probably would want to read the chapter 1 and 2 as well. And then the other chapters are kind of going into technical detail. But what I do is in each chapter, I have an introduction to the chemistry or the biochemistry you need to understand the contents of the chapter. So I try to give background information, so if you want to know the point of the book, the introduction in the concluding chapter is probably what you want to focus on. And then the rest in between, sample it and read it, and pick up what you can. In some, places, it's going to be more challenging than others. I purposely wrote the book to be semi-technical because nobody's really established the idea that there's an anthropic principle in biochemistry. So I see the book as really a scientific book as much as a Christian apologetics book, where what I'm trying to do is even establish this idea. And so I have to go into some technical detail to even to even show the legitimacy of the idea, right? And so if everybody's familiar with Hugh's book, Creator and the Cosmos, right? And Hugh wrote that book, and it's lay accessible. It's a really well done book, and it's a very impactful book where he's really introducing the lay audience to the idea of the anthropic principle. But he was able to write the book that way because Barrow and Tipler wrote a book a few years earlier called The Cosmological Anthropic Principle, where they go into the technical details showing that the anthropic principle is actually real, right? And there's no book that exists like that, like the Barrow and Tipler book. And so what I'm doing with Fit for a Purpose is essentially writing a book that would correspond to that book, where, so it's really not a book that corresponds to Creator and the Cosmos, but to the Barrow and Tipler book, if that makes any sense.
No.
I think it does. Thanks for answering my question.
But, let me say this, as a biochemist, I had a ton of fun writing that book. And I actually walked away from that exercise actually having a deeper understanding of biochemistry. I got my PhD 35 years ago and have worked in biochemistry in various ways, some in R&D, before joining, RTB, and then, still continue to study biochemistry. And I can tell you that the process of writing that book and doing the research for that book is I developed a deeper understanding of biochemistry. as a result of that. And what I'm beginning to see come out of it are some kind of unifying concepts. You know, that work that Banvanar and Martin did, where they looked at chain geometry and hydrophobicity, where it was geometry and again, hydrophobicity that seemed to be determining protein folds. You see that same thing when it comes to membranes. It's molecular shape, geometry, and hydrophobicity that explain cell membranes. And it's when you get to the metabolic intermediates, it's the geometry of the intermediates and their hydrophobicity that explains why the intermediates that we see in the cell are the ones that are used. And so what's emerging is this concept that shape and water solubility or hydrophilicity, hydrophobicity have incredible explanatory power. And I didn't realize that until I wrote this book, that this seems to be a unifying theme. And what's significant about that is it means that if you're talking about geometry, shape, molecular shape, and hydrophobicity, these are physical chemical properties that are arising out of the laws of nature itself. And it's remarkable that those two concepts applied to molecular systems can suddenly explain why biochemistry looks the way it does. That's crazy to me.
Wow.
That you can simplify biochemistry to that degree. That to me is where you start seeing I think the eeriness of the biochemical anthropic principle. It's absolutely eerie.
I had a quick technical question, if I could, Fuzz.
Sure.
I keep getting asked this question by a variety of people, including some RTB scholars, or not scholars, but chapter presidents. And that is metalloprotein complexes. So metals that are held in place in a protein complex. So think of things like hemoglobin, for example, that has an iron ion in the middle, and cyanocobalamin, which has a cobalt ion. Where do the metals come in to the proteins? Is it just purely electrostatic attraction? It can't be, because you'd get all kinds of other anions and ions, cations competing for that spot in the protein. So how do they get established? Because they're obviously critical to that quaternary protein structure to function.
That's a really good question. I've never studied the biosynthesis of metalloproteins to know how the particular metal cofactor is actually introduced into the to create the holoenzyme, right?
Yeah.
I don't know that
I can't find anybody who does.
Yeah, there's got to be, I'm wondering if there's something analogous to a chaperone, right? For example, I know that iron is complexed in a protein called ferritin, right? You don't want free iron, or, floating around. It's always complexed, either to hemoglobin or myoglobin or to ferritin, right?
Yeah.
And so there must be some mechanism by which ferritin would be transferring an iron that it's binding, as a store to hemoglobin or myoglobin as they're forming it on the ribosome. So I would suspect there's got to be some kind of an analog to a chaperone or something, right? But I don't know. I just never have studied that.
Well, I think the only reason I'm mentioning it to you is because I think it's another fit for purpose argument that maybe, you could take away and consider and put into the next edition of your book. I don't know, but it just seems to me remarkable that these ions have to be what they are. They can't be anything else. And when they are something else, the protein is dysfunctional. And you get all kinds of metabolic diseases arising. So
Yeah,
I find that fascinating.
yeah, I suspect you're right in terms of, kind of a fitness for purpose. I mean, that would be a really interesting exercise to look at the different types of metals, that are used in proteins. And again, these metals have different properties that are just right.
Yeah.
Something that was a recent aha moment for me is the idea of these iron sulfur clusters. It turns out that these iron sulfur clusters are showing up everywhere. They are obviously in the electron transport chain, right? Where you can create these local chemical environments that affect the redox potential of the iron center. But they actually are showing up in a lot of proteins that interact with DNA as well. DNA repair proteins, and even in things like DNA polymerase and the primase that's involved in DNA replication. They have these iron sulfur centers. And so these things are showing up everywhere. And so it seems like it's a very versatile metal cofactor that is used pretty widely. And so that may be another place where there's like an anthropic coincidence. There's actually a guy that just joined our scholar community, and he sent me an article that I haven't had any time to read, but he's actually an inorganic chemist. And he was taking a look at, I think some of the things that you're looking at is that the types of metal ions that you see in biochemical systems. But yeah, thank you. That's a great suggestion.
I have a question.
Yes.
It's been 40 years since I did any work in biochemistry, so I'm very not on top of the issue at all. But you said something. You were talking about the geometry and how that led you to some profound understanding. Could you go over that again? I didn't quite catch that.
Yeah. So, Badbinar and Martin come up with this idea of a folding parameter, right?
Yeah, right.
And it turns out that one, with the folding parameter of one, is this sweet spot where you get, the just right diameter relative to the distance of the interaction of the chain itself. You get this just right regime that gives you spontaneously the folds that you see in proteins that are the just right folds. And so it's amazing that the geometry of the peptide backbone is essentially one. So that if you kind of take the peptide chain, the backbone of a protein, right, and you put in like a space filling structure, the average geometry of that backbone relative to the distance that the functional groups on the protein chain are from one another when they interact is essentially one. That's crazy to think that you can create that these two, that amino acids, when they react, form basically a backbone that gives you a folding parameter of one. It just can't be, you just can't be lucky that way. This seems like it goes far beyond just luck. Right.
Okay.
It's a coincidence, but that coincidence seems to me to be pointing to something much deeper in the structure of biochemistry. But it's that idea that it's the geometry of the chain and what's determining the interaction of the chain with itself is the hydrophobicity of the amino acids, so that the chain is folding in such a way that those hydrophobic R groups are being buried in the interior and the hydrophilic R groups are being exposed to the water. So it's chain geometry and hydrophobicity that seem to be the two parameters. And likewise, when you look at the structure of phospholipids, it's the,
That's the one, yes.
yeah, it's the high, phospholipids have a hydrophilic head and a hydrophobic tail. And so it's that hydrophobic tail and the hydrophilic head lead to the spontaneous formation of essentially either bilayer structures or micellular structures. And what determines whether it's a bilayer or a micelle is actually the geometry of the phospholipid. If it is,
That's it, all right.
yeah, so if it is a cone shape where you have a very large head and the tail, a hydrophobic tail kind of forms a cone, that actually packs those molecules packed to form a sphere. If you have an inverted cone, they wind up forming what's called an inverted micelle. It's only when you've got a cylindrical shape that you actually get bilayers that form. And that cylindrical shape is based on something called a packing parameter, which is, off the top of my head, I don't remember but it's essentially determined by the volume of the head group, the volume of the tail, and then the length of the tail, right? And the diameter and things like that. So there's a number of geometric parameters that essentially define the packing parameter. And again, off the top of my head, I don't remember what the equation
Okay,
is.
that explains it. Yeah, I missed it.
Yeah. So, but again, what's remarkable is it's the property of hydrophobicity and the geometric features of the molecule that can now explain why you have phospholipids as the membrane component, why it's not fatty acids or some other materials, right? Why it's got to be phospholipids, right? And
thank you for that. Yeah, that's the idea of the geometry. Yeah, I wanted to get that straight. Thank you.
Yeah, it's pretty amazing when you think about it.
Here's a question that may complicate the issue. You talked about there's only a limited number of ways of folding a protein, but I also heard that in the cell there's molecular machines that help the protein to fold a certain way. So does that complicate things, or?
No, it doesn't, because you're dealing with it doesn't, because what the chaperones are doing, and there's two different types. There's ones that bind to the protein chain and kind of stabilize it so it doesn't improperly fold before the entire protein chain is folded. And then those chaperones begin to dissociate in such a way to allow the protein chain to fold. Or we have these larger barrel-shaped structures, chaperonins, that kind of form a cavity where the protein can go inside, and in that space adopt its folded structure. But in both of those cases, those chaperones are not determining the final folding. They are just simply helping the protein attain the minimum energy structure, right? They themselves are not actually determining how the protein folds. They're just creating a protected space that allows a protein to fold in the way that it needs to fold, if that makes any sense. So, in chemistry, you talk about the difference between thermodynamics and kinetics. So if a reaction is thermodynamically permissible, it means that you're going from a higher energy state to a lower energy state. But it doesn't tell you how fast that process will go, or even if it will go spontaneously. So for example, diamonds are not the thermodynamically most stable form of carbon, it's graphite. But diamonds don't necessarily go to graphite spontaneously. If they do, it's a very, very slow, imperceptible process. So even though thermodynamically diamonds should turn into graphite, kinetically the pathway it requires such a high energy of activation that until you ignite the diamond, set it on fire, it's not going to form graphite, right? And so that's a situation where the thermodynamically less stable product exists because of the rate of reaction is too slow. So likewise with proteins, the end product, the minimum energy state is where that protein chain will spontaneously fold to. And I'm using spontaneous in thermodynamic terms now. But how do you get there? What's the pathway? So when you talk about the pathway to go from state A to state B, that's where chemical kinetics play a role. And so what these chaperonins are doing is making sure that during that folding process, the protein doesn't get trapped into some kind of localized energy minima, but rather it's able to explore all the folding space properly so that it can hit the true energy minima, right? And so that's what the chaperonins are doing, is they're facilitating the process. They're not actually determining how the protein folds. Does that make sense?
Yeah, thank you.
Yeah.
I remember a talk by James Tour talking about the chaperones, and that to me would be one of those eerie things, that how can the chaperone exist prior to the protein folding properly? It's, you know, I wish, Fuzz, you could list all the eerie things you've come across during your studies.
Yeah, well, you know, I mean, the chaperones are this, you know, chicken and egg, you know, system,
Yes.
right? You know, and here, you know, when you think about protein synthesis, you've got the queen mother of chicken and egg problems, because you can't get proteins without proteins, right? So the proteins are involved in transcribing the DNA to make messenger RNA. They also are involved in transcribing the ribosomal RNAs and the transfer RNAs. If it's a eukaryotic cell, the proteins are needed to splice the messenger RNA. The proteins are then playing a role in the nuclear pore structure that is facilitating the transport of the messenger RNA to the cytoplasm. Ribosomes are made up of proteins, right? And then once the protein is formed, you have these chaperones that are playing a role in helping it to fold. And so if any one of those proteins is not made properly, then you can't get proteins to form properly, right? So you wind up, if the whole system isn't in place all at once working perfectly, you wind up in this auto-destruct cycle, right? I mean, just use ribosomes as an example. In order for ribosomes are made up of proteins and RNA, right? And so if you don't have high fidelity protein synthesis, then the next generation of ribosomes are going to be less effective at producing desired protein products, which means that the next generation of ribosomes are even going to be worse. So you wind up in this auto-destruct cycle. And the same thing is true, you know, for every step of that process, for transcription, for modifying the transcript, for transporting the transcript, you know, for the chaperonins. So, you know, you can't bootstrap that system up into existence. It's got to come into existence all at once. And it's got to be functioning at the highest degree of, the highest level of optimization at the get-go. Otherwise, you're in deep trouble. And people have done calculations, and you can show that the error rate for protein production, when you put all this together, there's all these quality control checks to ensure that everything is done just right, that in turn involve all kinds of proteins, right? So you have proteins doing the quality control checks to make sure that all these steps are happening in the just right way. People have shown that the error rate is highly optimized so that it is at a low enough error rate so that you can produce a protein with 1,000 amino acids at about a 90% rate of accuracy. But it's not so optimized that it would require the whole process of protein production to slow down to the point where you wouldn't be able to produce proteins fast enough for life to exist. So you have this balance between producing proteins with just right degree of accuracy so that you can produce them fast enough and proteins that are large enough to ensure that most proteins are going to be produced accurately, right? So, again, so you see fine tuning in the error rate, and then you see fine tuning in, for example, you just see fine tuning all through the process.
Well, thank you, Fuzz. We kept you a little longer than you probably intended, but thank you for all your answers to all of our questions.
Yeah, glad to do it. And again, thanks for letting me join just a few minutes late. That was a real help. So I appreciate your flexibility.
It was well worth the wait, let me tell you.
Thanks, Buzz.
I wish we had a weekend with you to ask me, just really with questions.
Well, a lot of the stuff that's in Fit for a Purpose, I piloted it when I developed this course in biochemical design. And so Don, you'll get a full dose of this as the instructor. So I actually, work through. So if you want to really get into this stuff, if you really have that desire for self-torture, take the biochemical design course, because we kind of step through this content and in the stuff that's in the cells design too. So,
all right. Well, I don't know, torture, it'll be frustration probably because I can't maybe get all the concepts, but anyway. So that's Don. Don gives that course, right, Don? I guess you're still there. I don't know. He's probably
No,
gone.
Fuzz gives the course. I just
Teach.
facilitate
No?
the students and support them when they have questions.
Oh, I see. You're the facilitator. Okay.
One of the things that I would recommend if you really want to get into some of this biochemistry is, for $20 or so, you can buy the dummy books, but the Biochemistry for Dummies is not a bad book. It actually gives you a pretty good background in biochemistry. I think sufficient enough that you could, grasp, like the cells design and grasp Fit for a Purpose. You could spend, $250 and get a biochemistry textbook, and you probably, for the cost differential, what you get out of the Biochemistry for Dummies would be more than enough.
Well,
So
that's
it's one
what I would
one of the
be.
textbooks that I recommend, I use.
Well, that's good to know. I mean, I like those dummies books. I've used them I'm in business now. I haven't been in biochemistry for 45 years, but those dummy books aren't that bad, actually. So I'm going to take you up on that, right?
Yeah. I mean, it gets you, it'll give you enough of a background that I think you would be able, to digest the content, in the cells design and then in Fit for a Purpose. So.
Mhm. Good, thank you.
Thanks again, Fuzz.
Yeah,
George,
thank you for
I-
having me.
Yeah.
All the best.
George, I see you had your hand up. You have a question? Or
No, I just say thanks for everything, and I gotta sign off right now. I'm behind. I gotta get something done for my
All right.
wife.
All right.
The
All right.
hobby thing.
bye, everyone.
Take care.
Goodbye.
Bye-bye.
God bless you guys.
Yeah,
Thank
God
you.
We'll see
bless.
you all
Thank
next
you.
month.
Yes.
Paula Rock is going to be speaking next month. He left a little while ago.
Okay.
See you all next month.
Bye-bye.
Bye-bye.
Cheers, guys.
See you, guys.